All right. 3.8, let's go. We're doing exponential functions here today. All right, this is our explore for the day. I just want to, there's a reason I took this little snapshot out of here. The remember portion. Okay, it says remember that, when exponential functions have this form where it's the starting value times the multiplier. All right, the starting value times the multiplier. Okay. Remember, like our starting value when we talked about this when as it pertains to like linear functions. All right, linear functions, your starting value was where you start on the y-axis. So we'll see if that's the same here when we get to exponential. So it says match the functions with the graphs. Again, if we look here, all right, well, we have 4 different functions here. Some of them are, on a decrease, so they're going to go increasing, okay? But the biggest thing we have to look for is that starting value. So if we look at some of these, this one looks to have a starting value of 10, this function has a starting value of 7, and this function has a starting value of 6, all right? I'm going to look for the starting value of 10 first. 10 looks like it's down. One second. All right, we're back. All right, so I'm looking for that starting value of 10 here. Okay, it looks like the starting value of 10 occurs down this bottom left. If you look here, starting value of 10, that's number 3. So this would be B. All right, starting value, remember, is another term for a y-intercept. Okay, we talked about that in our last unit. Now let's look for a starting value of 7. Okay, it looks like that is here, crosses our y-axis, that's 7. So this is C. I'm going to look for a starting value of 6 next. It looks like that's that last one. So that's D. And then process of elimination, this is A. Okay. Now, let's keep going. Where does the starting value appear in the exponential function? Or where does the starting value in the exponential function appear on the graph? It's the y-coordinate or y-intercept. Describe the value of a multiplier when the y values on the graph are increasing. Describe the value of a multiplier when the y values of the graph are decreasing. So if you look here, C applied to this function here, and you can see our multiplier there is 2. So with a multiplier of 2, it looks like it's going up. If you look at part B, it's an increasing graph. If you look at A and D, our multiplier is less than 1, so we had decreasing. Okay, so that's an important thing to remember, and we're going to talk about that more. But I'll say something like multipliers greater than 1, the y values increase, or multipliers less than 1. Think about that. I'll show that again. C and B, all right, the multiplier is 2 and 3. Our y values are increasing, okay, as x is increasing. A and D, our multiplier is 1/4 and 1/3. Our y values are decreasing, as our x values are increasing. All right, let's make that blue. So let's keep going. So discover for today as we work through the sections, or as we work through the section, can you tell the equation of an exponential function if the graph will be increasing can you tell from the equation of an exponential function if the graph will be increasing or decreasing? And can you use a starting value and rate of change of an exponential function to sketch its graph? All right, so exponential functions. So if we consider this exponential function 3 times 4 to the x here, We know that it is exponential because it follows that format of the starting value times the multiplier to the x. How do I know if something's exponential? Really, the exponent is going to be your variable. That's how you know. You see that exponent, our variable is our exponent. Okay, that is different than something like this: y equals 3 times 4x or 3 plus 4x. Both of these functions here in blue, those would be linear because our variable is not our exponent, it's just being multiplied to our constant, okay? So it just says your starting value is 3 and your multiplier is 4, which tells you that our y values are quadrupling, okay? Use information to create a list of ordered pairs. So I did that here for you, all right? At 0, y is 3. Remember that anything to the 0 power is just 1. So if I have a multiplier of 1/4, 1/4 to the 0 power is 1. A multiplier of 500, 500 to the 0 power is just 1. And like it said, our multiplier is 4, so we're quadrupling. 3 times 4 is 12. 12 times 4 is 48. 48 times 4 is 192. So this is how you're going to be able to tell if it's exponential. If there's a multiplier, a common ratio you may have heard last year. The y-intercept is the 0.03, and that's our starting value. Wait, where does our starting value come from? Again, it came from this 3, the 3 right here. All right. And then when x is 1, yada, yada, yada. I just kind of talked about all this. All right. Likewise, the decrease is a factor of 1/4. So if I have -1, I would have gotten 3/4 because that's our ratio. If we're decreasing. So if I'm going down here, -1, -2, -3, -4, etc., dividing by 4, dividing by 4, dividing by 4. If I want to work backwards, okay, if we're working backwards. Obviously, if we're increasing, we're going to multiply by 4. Okay, plotting a few points using knowledge, exponential, yada, 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 is enough to sketch it. This is what the sketch looks like. All right, like the equation of a linear function, there are two important numbers of the equation of an exponential function that can be used to draw it quickly: the starting value and a rate of change. All right, we'll talk about that rate of change here soon. Here we go. So let's talk about exponential functions. Exponential function can be represented by this equation. Again, this equation continues to come back. All right, A is that starting value, like it says here. A is the starting value. B is your multiplier. A must be a non-zero number. Okay, the variable B must be positive. That's always going to be positive, but it can be between 0 and 1, or it can be greater than 1. Okay, it's not going to be less than 0. It's not going to be less than 0. If we have a fraction, so a number between 0 and 1, or a decimal that's less than 1, our graph will be decreasing. This goes back to, which is kind of like exponential decay. So this goes back to our discussion when we talked about percent increase and percent decrease. This is why we did that. All right, we are building on that percent increase, okay, and decrease. Again, in this general equation, if there's enough, whatever this A value is, that's going to be our starting point. And then I'll do A times B to get my first point. Let's look at one. So I have 2 as my starting value here. 2 times 5 is going to be 1 comma 10. Does that hold true? Yes, it does. I apologize. Yeah, so we see here that 1 comma 10 is actually a point there, and it's going through that. All right. Now this one's going to be a little bit tougher to see. I could do, 4. We could see that 4 is that starting value of our y. If I do 4 times 0.42, I get 1.68. So 1 comma 1.68 will be that point, which is about right there, and it looks like it's to be true. All right. So let's talk about it. Let's talk to it. So remember, we can interpret a multiplier that we can interpret the multiplier to understand a rate of change in an exponential function. I want you to read that. It says that multipliers can also be interpreted as a percent. Okay? So a multiplier of 2 is the same as multiplying by 200% or increasing by 100%. Multiplier is a decimal. The rate of change is often interpreted as a percent. So suppose as an exponential, suppose y is an exponential function of x, initial value, there's our starting value, 7 and a 10% increase. So this comes back to that percent increase. Remember, when we have a percent increase, our multiplier is going to be greater than 1. So if it's a 10% increase, 10%, remember, is written as 0.1, like that, 0.10. Okay? So if my starting value is 7, that's going to be y equals 7 times, if it's a 10% increase, then that's going to be 1.10 to the x. Okay? Remember, if it's a percent increase, our multiplier will be greater than 1. Here, in this next problem, in part B, still have that initial value of 7, but now it's a 10% decrease. So it's going to start the same 7 times, but since it's a percent decrease, it'll be a number less than 1. So I'll do 1 minus 0.10 and get 0.9. All right. This came back. This is kind of from, this stuff is from first semester, that percent increase and decrease. Let's look at number 4. We're going to do number 4 together, and then we'll come back as a class to do 5 and the rest. All right, for each exponential function, why don't you read these bullet points yourself? All right, so let's look at this first function here. I can tell you that it's going to be exponential growth because this number is greater than 1. So our first bullet point, all right, the second one, since it's greater than 1, that's going to be increasing. Third one, our starting value is that 8. Write that as an ordered pair. The multiplier is 1.1. Our rate of change is 0.10, or we call that 10%. So that's how much over 1 it is. And then we want some points on the graph. Well, I know that 0.8 is there. And then 1 comma, if I do 8 times 1.1, I get 8 point, was it 8? Yeah, 8.8. So we're able to get all this information just by looking at this equation here. Okay, so now comes the time to graph it. So 0.8 is a point, and 1 comma point, or 8.8, which is about right here. And this graph can be hard to draw. It's going to look something like, as long as you have it going through those two. All right. Why don't you try the next one? You try part B, all right, and then I'll talk through it afterwards. So pause the video and try part B. Right, here we go. So this is an example of decay, exponential decay, because our multiplier is less than 1, which means it's going to be a decrease. Our starting value is 5, which remember comes from right there. Our multiplier is 1/2, which comes from right here. There was a 50% decrease. How do I know? Because 1/2, remember, can be written as 0.5. It's the same thing. So that's 0.5 less than 1, which is just 50%. And then I got 2 points, 0, 5, and then 1, 2.5. Remember, I get this 2.5 by doing 5 times 1/2. So my graph should look something like that. Something like that. All right. There we go. All right, for this number 5, I'm going to ask you to head back to the whole class, and we'll see you there soon.